Hi, welcome to the Signal Path. In this episode I wanted to show you a very quick repair of an instrument I just purchased. I actually wasn't planning to make a video, but I was doing a review on a Tektronix instrument and I wanted to do some power quality measurements, but I don't really have a power quality analyzer in the lab. So I did a quick eBay search and I found a Fluke 43B, which is this unit. Right over here you can see Fluke 43B written over here, and this is a power quality analyzer. This is a fairly capable unit and it's been around for some time, so it's not a new one, but I bought it as a broken one because the LCD screen was broken. So I thought, oh, we'll fix the LCD screen or replace it and so on. Little did I know that these LCD screens are really hard to get a hold of. And here's the LCD screen from the unit itself. It had two distinct problems. One was that these lines had developed on it, and I actually don't know what causes these lines. It almost looks like an EST discharge, but once these lines are developed, basically it's gone because whatever pixels over here is completely broken. It cannot be polarized anymore and it doesn't work at all. It cannot be fixed. Now the other problem was lines developing across it, and those lines obviously have to do with the column and row drivers, and they tend to happen because of the connection between the LCD screen itself and the board that's at the back of the screen. Now I have already taken the ribbons that go across so you can see clearly what I'm talking about. These are all the traces on one side, row or column drivers, and there's a whole bunch of traces on this side, and there's a ribbon that folds across over here and a ribbon that goes over the screen over here, and I'll show you in the replacement that I have what exactly that looks like. And once the connection there is disturbed, you're going to get those missing lines. Now there are people who can replace this, and I'll show you that as well. But once that ribbon is dead, you kind of have to take it off and put another one. That's really quite challenging to do. You need quite a bit of experience to do it. You need a replacement ribbon. You need to clean all that off. It's a lot of work. And the reason people put so much effort in it is because the replacement LCD screens from Fluke themselves are like almost $600, which is just absolutely insane for a 240 pixel by 240 black and white LCD screen, which is ancient. But anyway, and you can see at the back the different ICs for the row and column drivers and the interface that goes directly to the unit itself. So I went ahead and I disassembled, basically destroyed it, just so I can take a look at it. And if I were to remove that, you can see, you saw some lines show up, and that's because of EST discharge onto the unit, onto the screen, which activates the lines there. And if I hold it at a certain angle, you will be able to kind of see through it, and that's because obviously the camera LCD, the camera sensor has some polarizers in front of it, so you can see that happening. And having said that, yeah, this LCD screen, there's the closer look at this really unusual effect that is developed there. Either way, that's completely broken. And here at the back we have the diffuser where light enters from one side, and this is a cold cathode type of LCD. Here's the cold cathode light fluorescent tube there that sits over here, and then the light goes in there and it diffuses across there, reflects back of the back surface and comes straight out, which then you would be able to see as a backlight. There's an old stuff nowadays, LEDs are everywhere, but this is how most of LCD screens used to be done. And so if you take that apart, then the rest of it is just basically nothing more than a PCB with just the row and column drivers on it. So I highly recommend, if you've never taken an LCD screen apart, take one apart, because there's so many layers and cool things in there that are on top of each other. You can even further disassemble this, because on the glass there are the different layers that do the polarization kind of glued on top of it. So there's a lot of cool things to learn by just taking it apart. So either way, even if I were to send this out and get the LCD screen repaired, this damage would never go away. So I said, hey, let's just go and find a replacement. How hard can it be? And no, very hard actually. And I searched around and I eventually found a company that does it. So let me show you. So the company that I found that does this is at scopemeterrepair.com, and these guys specialize in repairing a whole bunch of different Fluke instruments, not just a Fluke 43B, but basically pretty much all their models. And they do different things. They fix also the analog inputs, and they do diagnostic and repair, and they can give you a cue of what type of problem your unit may have. So there's a lot of things they do, but as I was saying, what I was interested in is these black lines to be repaired. You could try to repair it yourself. It's just a big headache. It's nice if to get it to somebody who has the experience, especially because these units still cost a couple of $1,000s. So getting them fixed is pretty good. I believe it's $195 to fix the lines. Now the reason I didn't want to do that is because mine had that other defect, so that was pointless. But it also happens to be that they sell a used version of the screen. Is still not cheap, but they sell used or brand new ones, which is basically directly from Fluke. And I purchased one of their used ones, and one of the nice things about getting a used units from these guys is that they actually looks like they either have repaired this before, or they are putting this sticker on it so that nobody else messes with it. And because they actually give you a full warranty on this, so any of the screens that you buy from them are under warranty for not developing those black lines. So it's kind of nice to know that if something happens, then they're going to replace them. You can see they have put quite a bit of work on this to fix this issue, and this seems to be so common that businesses exist that basically handle this. So if you're running into one of these issues, I searched for a long time before I found it. So scopemeterrepair.com, give them a try. Like I said, these are still pretty expensive, but I would say cheaper than completely losing your unit, your machine over there. So anyway, so let's go ahead, take a little bit closer look at the components of the Fluke 43B, and then we'll put the LCD screen back in there. Hopefully it will come back to life, and then we can do some measurements with it. So the construction of the Fluke 43B is actually quite nice because all of the electronics is embedded in here, and you don't even need to take this apart in order to service the LCD screen or the keypad, for example, or change the battery. And you can see the infrared ports, the AC charging port, as well as obviously the input signals to the unit itself, the keyboard, LCD screen, and the backlit. Everything is there. Those are the main interfaces of this unit. Otherwise, it's fully enclosed. So we'll take the top of this off so we can see what's going on inside it. And we should find some of the very similar, familiar build and the design of this, which is quite similar to their scope meter, because essentially what this is doing is that it's sampling current and voltage at the same time and then doing analysis on that. So we're basically looking at like a scope meter essentially. So they are building it on top of their existing technologies and getting all this extra functionality. This is very geared for power analysis, but that's basically what's going on. The battery is nickel metal hydride, and it's a 3000 milliamp 4.8 volt battery, and all these little pieces like the battery, the ribbon for the keypad, and so on are also replaceable, and you can buy them from the website scopemeterrepair.com. They also carry this component, which is nice, and you can see multiple wires coming out of the battery for balancing circuitry, which is all built onto the main motherboard that is in here. So one of the first things I'm going to do is I'm going to put this used LCD screen back over here so that this portion is completely closed, clean it up, make sure there's no dust behind it and so on, so that we don't get any particles there. Other than that, the screw is actually nice that it comes with one of these LCDs. Oh, interestingly enough, this one is soldered, this ribbon cable is soldered directly onto the back of this, whereas if you look, the original one had a connector. I wonder why that is. Perhaps they took this off and just soldered it on there to replace it, or maybe this connector was broken on that particular one they sent me. But anyway, interesting. So let's go assemble that and we'll take a look at this, take it apart and see what's going on in it. And here's a look at the main motherboard of this unit, and this has a very familiar design. If you look at my scope meter repair that I did a long time ago, you will recognize some of these components because they're used among a whole bunch of different Fluke instruments. And you can see here the AC line coming in is a 19 volt or so power supply. There's a hybrid filter there, which is an LC combined unit in here. You can actually buy these separately. And here we have the main power controller IC, which again is used in all the scope meters, which is responsible for the DC-DC converter. You can see some of its components here. This is for the flyback converter for the cold cathode tube over here. This is the main DC-DC converter for the unit itself. And this guy handles the battery charging, making sure the power supply is connected and switching between internal and external battery, operating the DC-DC converters and so on. So it's a very common component. The main processor, which is a Fluke rebranded Motorola processor, runs the entire operating system, so-called, of this unit and does all the calculations and computations. I see some memory over here, perhaps some flash memory over here. These ICs that you see, these are actually Philips branded ICs, and these are, I couldn't find any specific data sheet for them. Again, makes sense because they're designed specifically for this instrument. And you can see two separate input channels coming directly from the outside, and the red one is coming from the AC line. That's where you would connect your voltage, and the black one over here is where you would connect to the loop for measuring the current, and the clamp for measuring the current, and I'll show you that in just a second. So you can see the difference between these two pads and the input protection, a vast amount of input protection that is embedded in here. You can see different capacitors, MOVs and resistors and so on, and different gaps in the PCB to protect against high voltages arcing across the PCB. Every input in this instrument is Cat3 600 volt rated, as to be expected. So that's why there's so much protection circuitry in there. And then the inputs are then processed by these two mysterious ICs, and some relays for range switches probably, and so on. The infrared port being over here as well. Other than that, it's really pretty straightforward. Everything happens in these couple of ICs that are specifically Philips rebranded for Fluke, so you won't be able to get much information, but the operation, is pretty straightforward in terms of what you would expect. You have input protection, you have some front end, and you digitize and you process the information to get power factor calculations and all of the other information you would want from this. So just wanted to give you a quick look at it so that we take a look inside. It's very nicely designed with different compartments and so on, all isolated quite well, as you would expect from a Fluke instrument. Only I wish they would use a better LCD screen so that this problem wouldn't be so widespread, especially for units that are going to be thrown around, designed to fall off the tables and being in harsh environments. You want a really solid LCD screen, and it's a shame that these guys, at least in the older units, didn't have that. So let's put this back together, connect the whole thing up, and see what happens to it. And here we have the unit. I put it all back together, and when the screen is off, it's quite reflective. You can see everything in the screen. Let's go ahead and turn it on, and there it is. It works really nice, and it no longer has the defects that the LCD used to have. So it's a perfectly working LCD screen, and it looks quite good. The backlight looks good. There's a couple of scratches on the main units on the outside, which is due to being poorly handled and so on. It doesn't really affect the performance. Maybe I'll find a way to fix them later. But the main front screen right now is showing us what the instrument is expecting in order to be able to do power quality analysis. And on channel 1, input 1 is expecting for us to give it the voltage, and on channel 2 it's expecting a current probe with a sensitivity of 1 millivolt per amp. And that can be changed, of course, in the configuration, but this is how it is configured right now. And in fact, I already have connected the clamp to it. And if you take a look at the clamp over here, it's this one right here, and let's take a look at it. Oh, it's this way. This is actually a Fluke ADI 500S, and this can go all the way from 1 amp to 500 amps. So this is a very high current unit, obviously intended for industrial application or even measuring current coming into your house and leaving it on somewhere where you can do long-term capturing of data. And this indeed is a 1 millivolt per amp pickup. Works all the way from 5 Hertz to 10 kilohertz. Obviously, it has to be AC because of the principle of operation. And the way these things work are quite straightforward. You're basically making a transformer. So you have one wire that goes right through the center over here, and that wire has to carry AC current. That's going to induce a magnetic field, and that magnetic field can be picked up by the coil that's wrapped around the cable in this way, and that's going to be converted to a voltage, and that voltage is then it's going to be the 1 millivolt per amp conversion, and then picked up by the Fluke 43B for analysis. Now, obviously, the best type of pickup is a nice continuous metallic round around the wire, but we can't do that because then nothing can be put through it because you'd have to cut the cable, and that's why they make a compromise and make a clamp such that you can open the clamp, slide the wire in, and then close it. And you can see over here that we have metallic pieces here and here, which are nice and clean and shiny, very flat surfaces, so that when you close them, they make a very good connection and essentially emulating what is almost a closed loop completely. So it's as ideal as it can be. And you can see the direction of the current is labeled over here. And so if your current goes in this direction, then it's going to pick up a positive value. If you flip it, it's going to tell you the current is negative, which just means it's going the other way. Now you cannot pass both wires through it, because then the magnetic field of the two wires will cancel each other out. It's going to read nothing under ideal circumstances. Sometimes they can be useful if you have your live and neutral lines going through here, and if you still see something, that means that there is some leakage somewhere, maybe going through your earth connection. Some houses are equipped with detecting that and automatically flipping the fuse out, so that means that you have some leakage somewhere in your instruments or in your appliances. You have some line or neutral line going to ground, which is, you don't want that because you want all the current being returned from the same lines. So that's another interesting thing that you can use to measure that effect under some specific circumstances. Of course, depends on the situation. So now what I want to measure, just do a very quick measurement of some of these fluorescent lamps that I have in the lab, because those guys are actually quite bad in terms of their power factor, and the reason is because of the way they operate, and I'm going to explain that hopefully briefly once we turn it on. So I'm going to go past my light that is right now on in the room directly through here, and then take a look and see what kind of waveform it's going to give us. And here I have the Fluke 43B in scope mode, so I'm essentially measuring the voltage and the current delivered to the fluorescent light bulbs in my lab. And you can see the waveform shape for the voltage, which is the nice sinusoidal one, and for the current right over here. Now the voltage tonight at my house is 125.6 volts. which is typical where I live, and the current being consumed 1.22 amps. And that's the average current. That's the current that you would see if you were to use, for example, a multimeter just in series with a wire to measure the current. That's exactly what you would observe. But look at the shape of the waveform of the current. You can see that it has these sharp pulses. And there's two characteristics. First of all, the peaks lead the main peak of the voltage ever so slightly. So you have some leading of the current to the voltage, and the sharp pulses mean that this current measurement is going to have a lot of harmonics in it, because it's going to take a lot of harmonics to produce a waveform that has these positive and negative pulses. We know where those pulses come from. It has to do with how the power supply of the fluorescent light bulbs work. As the voltage rises, the power supply all of a sudden kicks in and sucks a lot of current from the grid in order to dump all that energy into the inductors inside, and then dump that energy back onto the fluorescent light bulb in order to create the light that we see. And then that current is very quickly extinguished, and on the negative cycle of the voltage you get the same behavior again. So you get this positive pulse, negative pulse, positive pulse, negative pulse, and it's going to continue on obviously forever as long as the light is on, and that is going to create a lot of harmonics. The harmonics are bad because the harmonics are going to show up on your power line. So not only are you going to see 60 Hertz, you're going to see all the other harmonics of the 60 Hertz. In this case, because the waveform is completely symmetric, it's going to have all the odd harmonics. So it's going to have a strong third harmonic, for example, at 180 Hertz, that's going to be there, and then so on the fifth one, and so on. They're all going to be on your line. And if you don't have good filtering on your, let's say on your audio equipment or on your lab instruments or some other stuff, you can hear humming, you can hear noise, you can hear interference. So having this dirty current on your power grid in your home can be quite bad. But unfortunately, with the fluorescent light bulbs and LED light bulbs, which are going to have the same problem, this is going to be a commonplace, and we have to be able to learn how to filter these, or at least be aware that they're there. So what this instrument is going to do is going to take that information and give us a whole bunch of power quality analysis. So let's go in that menu and see what that is going to look like. Now if I go under my power measurement here and press enter, there we go. Now I get all the information back. I see my voltage waveform here again, and I see my current waveform over here again. Obviously my voltage waveform is going to be very nice and clean, because it's going to take a lot to damage that, because that's the voltage coming into the house. It's going to look typically fairly good unless you're doing something really terrible, and I'm not really consuming a lot of power, as we shall see. Now the actual amount of power that I'm consuming, the real power, is going to be 80 watts, and the reason it's so high is because I have several very bright fluorescent light bulbs that are all consuming at the same time. That's why it's so high. But the apparent power, based on the shape of the current and based on the amount of current that's being taken out of the grid, is going to be 150 watts, which is quite a bit higher. But if you look at my different types of power factor, there's some other interesting things to note. The displacement power factor, which is not taking into account the total harmonic distortion of the current measurement, is going to be quite good, because the leading of the pulses with respect to the main power is not really that significant, because you can see that this peak is almost at the same point as this. If it was exactly under the main peak of the voltage, the displacement power factor would have been 1, because we are really lined up. We have 0 phase offset between the current and the voltage, so the cosine of that is going to be 1, and it's going to have no problem. But there's a little bit of leading here, and that's why the displacement power factor is not 1. But the total power factor is only 0.5, and that because the total harmonic distortion is taken into account, and that is going to reduce our total power factor significantly. And this instrument can show us that total harmonic distortion problem. I just have to go to the next screen. And here, in the next screen, is going to tell us exactly the frequency content of all the harmonics that go into the current measurement. And check it out, the fundamental tone being at 60 Hertz, right over here, you can see that it has almost all the current in it, 0.67 amps. But check it out, the THD is 82.4%. That's horrible. And you can see the relative power of all the harmonics. And it goes all the way out to the 21st harmonic over there. As I mentioned, it's not going to have power in the second harmonic, and I can move it over. Check it out, second harmonic, nothing. There's no power going through the second harmonic. Go to the third harmonic, and now you can see again lots of current going through its third harmonic being at 180 Hertz. A lot of power there. That's why your total power factor is so poor. And as I also mentioned, the voltage is going to look very good. The THD and the voltage is 2.5%, is basically pretty much perfect for a voltage measurement inside the house right now. So it's pretty good. You can't really disturb that much. But Nonetheless, you can see the problem with the THD, and if I go continue on back onto this screen, maybe go to the next one more time, and that will determine the difference between the displacement power factor and the total power factor. Anyway, that's all I wanted to say. The reason I decided to make this little quick video is because I got a lot of feedback about people asking me to make, different videos around what's happening in the lab, because there's a lot of things that I do that I just don't film because I feel like either they're too short or they may not be too interesting, because my videos are typically very long. They have a lot of technical content, they have a lot of experiments in them, and they take a long time to produce. But if you guys like this type of short little videos, let me know. I'll try to make more of them as I do things around the lab. Right now I'm working on a review of a Tektronix synthesizer, which would be very, very cool because there's got some really cool wireless experiments in it, and I'm excited to finish that and post it. So let me know what you think, and hopefully I'll see you soon.